So it's only 2 days ago that I published the video about extruding tubing on a 3D printer. And you guys gave me loads of great feedback on it. The most dominant one, using a peristaltic pump. So good for you that I already did my homework. So let's quickly put something like this together. So welcome to another video on this channel. My name is Jan. And today I tried to pronounce peristaltic pump, so you don't have to. Enjoy!
Da 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 da.
So just as a quick word, after let's say my Bamboo Labs incident lately, I kind of went back to the roots and got my hands on another Prusa printer. This is the Core 1 Plus, and this has been working really reliable for me. It's a great addition to the Core 1L. So what I really do enjoy, these parts are printed from a polycarbonate blend carbon fiber mix. It does print really reliable, and also it is stiff and heat resistant and all that good stuff. This has probably become one of my most printed filaments lately. I think I found some settings that work. So if I have this drill here attached to it, it does at least spin, and we're shy of the front plate, so that will keep the bearing centered. Let's put some fluid in it. That does work. The question is, does it work with air? So watch the flame. It definitely does something. Of course, we were expecting some kind of a pulsation. Let's have a look at the flame. All right, let's put air in and see how fast we have to move to go with the lowest setting of this drill. So I can't really run this any slower, but I have to run it this fast in order to match kind of the needed volume of air to our extrusion speed. The question is, if I put a stepper motor here and control it very precisely, does the stepper have enough torque to actually run this at this speed? Because this here is not looking too bad. This Makita drill does have a lot more low-end torque, but this is again the lowest it will do. Apparently these drills do have some kind of detection. I had to reset the power button that it moves again, and this kind of messed up this result here. definitely the right direction we're going here. Let me find a stepper. This is 2 amps, which is on the edge. With 3 amps it does kind of work, but I have no idea how long this guy will do that. So what we got going here is not ideal, but it will probably also deliver some data. I have synchronized the extruder with this pump, and if I run an extrude command, this is 100% speed. I've set up a macro that will let me dial in anything between 20 and I think 1000% of that. And this is 20. So now it does run way lower compared to the extruder. And let's do one last with, let's say, 400%. Same extrusion speed. It needs a second to get up on speed. But yeah, this is kind of like my starting point here. So let me try to find some values for a standard extrusion width of a tubing, let's say 4, 5, 6 millimeters, where we end up, what kind of relation is between these two. Let me try to capture some footage here before this thing melts. In theory, this PC blend should be able to withstand 110 degrees, but I think this motor is approaching that. But other than that, I think we're quite nicely settling in. What we have to take into account is that the pump in this current configuration is not reliable, as in I had to dial this in very loosely, so the available torque from this NEMA 17 stepper is enough to make the full revolution. Right now I'm at 225% synchronization speed. Let's go to 250. So now this runs even faster. And in the same moment you can see that the resulting tubing is blowing up more. So a few things have happened. First of all, we have like a dent in here, so air can escape, and there's no way to inflate the tubing as long as we don't pinch it somehow. Eventually it will find enough back pressure to inflate again. If we are at a crest, the distance from the last extrusion to the nozzle is shorter, therefore it has less time to cool and is less viscous. Therefore, the incoming air has more tendency to inflate it right at that point and not later at the extrusion, if that does make any sense. So right now we're kind of in this positive feedback loop where a crest will deliver the next one even more amplified on that. Yeah, this is kind of the best I got so far, I guess. In terms of consistency, I did just change a few things here and there. I think here I went from 50 to 60%, trying to, like, if I can catch up to the nozzle. But apparently the closer I get to the nozzle, if the layer like less than 10 millimeters or something, it kind of bursts pretty easily. So probably I need to go down with the temperatures again to close that gap. Layer adhesion has become a lot better. As said in the previous video, it is a combination of the temperature of the new material hitting the old layer. But this has some kind of flexibility, but does not tend to break easily. Alright, before I show you what I want to follow up that with, let's talk for a brief second about our today's video sponsor, which is PCBway. And yeah, I have to keep thanking these guys on and on for all the incredible parts that they have delivered for these kind of awesome projects here. Not only did they provide a lot of 3D printed things for the Minuteman machine, but again and again they have shown their excellence in SLM manufacturing during these projects, and all of these parts that will possibly be featured in a future episode. So if you're in desperate search for manufactured parts, go and check out the PCBway website. They deliver all sorts of goods, starting from PCBs over to anything that will come off a lathe or a mill up to 5 axes. And as shown here many times before, they do all sorts and flavors of 3D printing. If you go on the PCBway website, you just have to upload your parts in whatever format you got on hand, select the desired quantity, as well as materials and surface finishes and tolerances and all of that, and you will get an instant quote as well as a lead time. And I can't overstate how much I love this service. It is dirt cheap, arrives in no matter of time, and the quality is kind of unmatched. So again, PCBway, thank you for sponsoring that content. Let's go right back at this guy. This is my first try at something, I have no idea what we should call that, non-planar tube printing, something like that. So it does vary pretty much everything. It varies the ratio of this guy in synchronization to the extruder. It does vary by 30 millimeters in Z height throughout a revolution, and then of course the extrusion speed as well. And it seems like that I just started to catch a bit and get consistent here. It really is a problem for me to get the start going. And at some height in the print it does get better. And apparently running this macro seems to be messing with the computational power of the Raspberry Pi here. Yeah, this print is also gone. Let me try if I can get that going from the very start. And that did not work. So I couldn't get a proper start, or let's say I don't have a recipe for getting this started all the way at the bottom. Which brings us to our main point, the peristaltic pump. Because what I always do is start an investigation and try to derive where are the main problems, and then find the easiest doable solution for getting some data on it. Because what I'm now certain of is that I was right with my assumption that pressure is a bad variable for doing all of this. It is rather controlling the flow. And what this prototyped and hacked together solution does is exactly giving me answers on that. If you're interested in that, this is all derived from a water pump built by Maximilian Puschmann on printables. He also added step files and I heavily modified it. If there is interest in this, I will upload this as a remix. But this is not finished as well. I would change a few things here and there. The issue with this approach in general is that it's meant for fluids. Because to get this gas tight, you need to get the clearances really spot on, and you then need huge amounts of torque on the motors, and still with loads and loads of improvements on here, you probably wouldn't be able to do it perfectly. Because what I found, depending on the speed this pump is running, the output will be different. It is not linear. And that makes it a problem for this concept. But this is not a problem. Because now that we know that we need to do it with some kind of mass flow regulated system, we can have a look at industry and choose components basically from shelf that will do exactly that, and they will do it with a known certainty. I could be sitting here for weeks trying to figure out graphs for flow data and all of that, just finding out a day after temperature changed, everything is different, and then the whole math doesn't work. And especially in a system like this, where you do have so many variables that need to mesh together, having one uncertainty just makes it way harder. There's temperature, pressure, viscosity, layer height, tubing diameter, you name it. There's just plenty of stuff that could go wrong. So what we're going to do now, we're going to keep this system, and I already put in 2 strains of TPU. I'm kind of chasing down the things you gave me in the comments, and a lot of people also commented on choosing TPU as a tube filament. And I already just extruded some into free air. I'm sure this is at least working. So let us try to resemble something like this and hopefully find out that TPU is doing a way better job at being expanded or inflated than this really low viscosity PLA is. It took me some time to get some dialing here, but this is TPU extruding. One thing up front, we would need some proper cooling. I would really like to do or go down with the temperature of the hot end, but I don't dare. I had some clocks before and I don't want to stop this experiment here. As you can see, there is no way of bridging something, so it does like cross this gap and then it takes ages to cool. And again, crests will be amplified and valleys definitely won't happen anything. Let me switch lenses here. And right now we're at 125% of synchronization. Let's go in 150. And yeah, the last line probably is a bit bigger than the previous one, but it is not as easy to distinguish as I would like to have it. But keep in mind, this is TPU, this is flexible right out of the gate. Therefore, if you make a sudden change of air velocity going in there, it is going to affect at least a few revolutions of this vase. Not just the last few millimeters extruded, which would be what we need in the future to make this foolproof and dynamic. And yeah, the second I started to experiment with the slightest bit of cooling, the extruder started skipping. You've probably printed stuff in TPU before. You know this squishiness of things. But have you seen this before? As we all know, with TPU the layer adhesion is great. I'm pretty sure I can extend this at least a third to 50% of the original in Z, which I haven't seen before. Of course, this is also incredibly light, and I would bet that a huge part of this is a continuous tubing. And by taking that entrance here, you can see that the whole cylinder is growing and shrinking in size. So I don't really know where this cuts off, probably here. I pinched it at some point during the print, I think with a camera lens this was. But yeah, this is pretty surely a continuous tubing. Alright, kind of wrapping this up. What did we learn here? So this is, I think, print 4 or 5 I made on the machine with dialing the tubing diameter by the pressure variable. And this is, I think, print 7 or 8. And in my experience, if something looks as close as to the desired result as this is something that will definitely work. And then lastly, we did this kind of exciting TPU print, which shows that the underlying principle is basically the same. I still have to investigate why I wasn't really able to get this blown up to the same tubing diameter as this one. Maybe this has some higher viscosity and the pump I have built is only able to produce tiny amounts of positive pressure and it's not able to inflate this. I don't really know. But yeah, this is probably a good point to have a look in the future. What are we going to do with this? Just like in the last video, and I read all of your comments on that, We still need to have some proper silver lining in the background. So let's try to find a reason to do this, and then we can get back at this topic. What I will do pretty much no matter what is going back at defensive publications on this topic. And by doing that, I want to make sure that all of the things that are possibly in there and still haven't been patented are available to the community and everyone out there for the eternity of time. So everything you post in the comments will be read by me and then ultimately published in some sort or the other, making it as hard as possible for companies, etc., to patent this away from us. And now, I hope you found this update interesting. This is just a few days after posting the initial video about the topic, so I had some spare time to go after your thoughts on it, and I highly appreciate the feedback here. So while this is going in the background, I will show you pretty much what we're doing, or what I have planned the next week. This is combining a precision toolmaker vise on this machine, because I think I want to do some injection molding. It has been done before, and I took great inspiration from it, but I think I do have some interesting thoughts on that that are not seen before. And I think also that it is possible with this hot end especially. And then ultimately, I can't put it differently, I can't sleep at nights because I have theories about speed printing. Yeah, so probably we'll get into that again. So that's it for an update. Everything you post in the comments will be read. Thank you again for all my patrons who contributed to me making this weird stuff here. Also, you'll find a link to the Discord somewhere in the video description, where there's a very open discussion about all of this. I'm posting there frequently. And yeah, lastly, thanks again for PCBway for sponsoring that content. My name is Jan, and I build stuff so you don't have to. See you in the next one. Bye bye.